Okay, so now we'll look at rationalizing denominators when they contain two terms. All right, so we have to discuss something actually. Um, if you have the sum of two terms, let's say two arbitrary terms like a and b, and you add them together, then you take the exact same two terms, a and b, and you subtract them, the difference. You have the sum and difference of the same two things. These two expressions are called conjugates of each other. So they're called conjugates. So whenever you're adding and subtracting the exact same two things, those expressions are called conjugates. Now, the nice thing about conjugates is that when you multiply conjugates together, a plus b times a minus b, you get a binomial because the middle term cancels. The two middle terms will cancel. You'll get a squared minus b squared, which is what we call a difference of two squares, a difference of squares. So when you multiply conjugates, you get a difference of squares. Now, the nice thing about that is that when the two conjugates involve square roots, for instance, the square root of 3, or let's say 5 square roots of 3 plus 7, right? That's an irrational number. But if you multiply that irrational number by its conjugate, 5 square roots of 3 minus 7, well, nice things happen because those are two irrational numbers. One happens to be the conjugate of the other. But when you multiply those two irrational numbers, here's what happens. We can even do it the long way. First times first would give me 25 square roots of 9. Outside would give me negative 35 square roots of 3. Inside would give me positive 35 square roots of 3. And last times last would give me negative 49. So we get 5 or 25 times 3. Those cancel out, which is why we only got the binomial that was a difference of these two squares, minus 49. Which squares? The square of 5 square roots of 3, which is 75, and the square of 7, which is 49. So the final answer then is just the rational number. What's this going to be? 26? 26. So 26 is what that product equals, which is a rational number. Let's use that fact. Let's say I say rationalize the denominator. Let's say I give you this. 7, or not 7, let's say 9 over 5 square roots of 3 plus 7. And I ask you to rationalize it. This isn't like the ones that you had done previously where there was a single term in the denominator. Now there's a binomial, two terms. 5 square roots of 3 is one term, 7 is another term. To deal with this, to rationalize this, what we do every single time is we multiply by the conjugate of that binomial. So we multiply by the conjugate of the binomial to create an equivalent expression. The conjugate was this. But you have to do the same thing to the top, otherwise it will not be equivalent to the original. So you multiply the top and bottom like that. When you multiply the top, you're going to get 9 times 5 square roots of 3 minus 7. I'm not going to distribute just yet because I know the bottom is going to be a rational number and I might be able to cancel factors with that 9 factor. So, I know what it is. It's 26. When I do that product on the bottom, it's just a 26. But 9 and 26 don't share any factors. So you could leave this as your answer because the denominator is now rationalized by multiplying by the conjugate. Or you could distribute and get 45 square roots of 3 minus 63 over 26. And that would be the final result. Alright, let's try another one. So rationalize the denominator. And what I want to rationalize the denominator of is, let's say, the square root of 5 minus 2 over the square root of 10 minus the square root of 3. And let's say I wanted to rationalize this denominator. Well, just like before, the goal, since there are two terms in the denominator and it's an irrational number, we want to multiply by the conjugate of that irrational number. So the conjugate of 10, the square root of 10 minus the square root of 3 is simply the square root of 10 plus the square root of 3. So you multiply the top and bottom by that, otherwise it won't remain an equivalent expression. We have to do the same thing to the bottom that we do to the top. Essentially, what we're doing is multiplying by 1. Everything in red just represents 1 because it's something divided by itself. So I FOIL both of these then. So if I FOIL the top, I get the square root of 50, this times this, plus the square root of 15, this times this, minus 2 square roots of 10, this times this, and then minus 2 square roots of 3, this times this. But I also have to FOIL the denominator. But the denominator, they're conjugates, so it's nice. I can use the trick. Remember that a plus b, when you multiply it by a minus b, you only get the difference of the two terms squared. It's a difference of squares. Well, I'm going to use that. So it's going to be the square of that, which is the square root of 100. The square root of 10 times the square root of 10 is the square root of 100. Minus the square root of that, which is the square root of 9. So this turns out to be the square root of 50 plus the square root of 15 minus 2 square roots of 10 minus 2 square roots of 3 over 10 minus 3. I can actually simplify that square root of 50, right? That square root of 50 I can write as the square root of 25 times the square root of 2 instead of the square root of 50, right? So that way I can break it down. So I break that down further into 5 square roots of 2 plus the square root of 15 minus 2 square roots of 10 minus 2 square roots of 3 all over 7. And I don't see any like terms in the numerator, so we can leave this as the final answer. Rationalize the denominator. Now the denominator is only the number 7.